Module 2, Lecture B, Dictionaries and Strings. By the end of this lecture, you will be able to use dictionaries to store and retrieve engineering properties by meaningful keys, process strings to clean, split, and format technical text data, and combine dictionaries, lists, and strings to build structured engineering records. Dictionary lookups, key-based retrieval. Dictionaries let you retrieve data by meaningful keys rather than by position. This is especially useful in engineering, where values like material density or yield strength are identified by descriptive names. Key-based access makes data easier to understand and matches how engineers naturally think about properties. Dictionaries let you retrieve a value by using a meaningful key rather than relying on its position in a sequence. This is useful when data may change or grow, because positions in a list can be easy to mix up. For a pump record with details like flow rate and pressure, named keys make the structure clearer, safer, and easier to manage. Dictionary keys act as clear labels for stored values, making data easier to understand, inspect, and debug. In engineering data, keys such as material strength, ratio, resistance, or voltage rating give context to each value. Using explicit keys helps keep technical records organized, verifiable, and useful as data moves through tools, scripts, and databases. Python code, key-based retrieval. Dictionaries let you retrieve values with meaningful engineering keys, instead of relying on fragile position-based access. In this case, a dictionary is used to store a single material record. A material record dictionary is used to store key engineering properties for a material. In this example, it identifies the material as 6061 aluminum and records its density as 2,700 kilograms per cubic meter. Using descriptive keys makes the material data easy to manage and retrieve. The material properties are stored in a dictionary for easy lookup. It includes yield strength of 276 megapascals, elastic modulus of 69 gigapascals, and thermal conductivity of 167 watts per meter Kelvin. The code retrieves key material properties from a dictionary using clear descriptive labels. It gets the material name, yield strength in megapascals, and density in kilograms per cubic meter. These meaningful keys make the data easy to understand and the code easier to maintain. Create a short, formatted summary that gives a material's name, yield strength in megapascals, and density in kilograms per cubic meter. This provides a quick, clear way to communicate key engineering properties. This example demonstrates how to look up values in a dictionary using descriptive keys. It prints a material summary with the name, yield strength, and density, then shows the available keys to indicate which properties are stored. It also retrieves the elastic modulus directly by its key, highlighting how dictionaries make data access clear and convenient. This script shows how a Python dictionary can store and retrieve material properties for 6061 aluminum using descriptive keys. It accesses values such as yield strength, density, and elastic modulus to print a short material summary and related property information. The main point is that key-based access makes engineering data clearer and easier to retrieve than relying on position-based methods. Meaningful key retrieval. Dictionaries are useful in engineering because they store and retrieve data using meaningful names instead of positions. Keys such as density, thermal conductivity, or maximum operating temperature make each value easier to understand. This turns data access into a clearer way to interpret technical information. Descriptive dictionary keys make engineering data easier to understand, share, and maintain. Clear names preserve context, so values like flow rate, motor power, or different temperature types are not confused. This reduces errors when data is reused later or handled by multiple people. Meaningful dictionary keys make data easier to organize and understand, especially in engineering uses such as test results or sensor readings. Well-chosen keys can make a dictionary represent a real object or event clearly, which supports analysis, reporting, and communication. Key names should be designed carefully so they are specific, consistent, and understandable to people working with the data. Python code, meaningful key retrieval. Dictionaries use clear, descriptive labels to retrieve values, which helps reduce confusion in engineering records. A simple pump specification can be modeled this way. A pump record dictionary stores key pump details using clear, descriptive labels. It includes the pump's equipment identifier, P-204, and its flow rate of 320 liters per minute. Meaningful labels make the stored specifications easy to understand. The code creates a pump specification dictionary with clear entries for key operating values. It stores inlet pressure as 185 kilopascals, outlet pressure as 460 kilopascals, efficiency as 78%, and motor power as 22 kilowatts, making the pump data easy to retrieve and understand. The pump record values are retrieved using descriptive dictionary keys, such as those for flow rate, outlet pressure, and efficiency percentage. Accessing data by meaning rather than position makes the code easier to understand and helps reduce errors. The pump's pressure rise is found by subtracting the inlet pressure from the outlet pressure. This pressure difference is an important measure of pump performance, and using clearly named dictionary entries helps retrieve the needed values accurately. The output summarizes key pump data by showing the pump ID, flow rate, outlet pressure, and calculated pressure rise. Together, these values identify the pump, indicate its capacity, and show how much pressure it adds, giving a quick view of its performance. Use the dictionary get method to safely read the maintenance status from the pump record. If the key is missing, it returns a default value of not recorded instead of causing an error. Printing this result lets the program handle incomplete data smoothly. The pump is described by its key operating properties: an inlet pressure of 185 kilopascals and an outlet pressure of 460 kilopascals, which define the pressure rise. Its efficiency is 78%, and its motor power is 22 kilowatts, indicating both performance and energy use. This script shows how a dictionary can store pump specifications using clear, descriptive keys. It retrieves key values such as the pump ID, flow rate, and pressures, calculates the pressure rise from inlet to outlet, and reports maintenance status if available. It then summarizes the pump's efficiency, demonstrating how meaningful keys make engineering data easier to manage and understand. Safe key access. Safe key access means reading dictionary data while expecting that some keys may be missing or wrong. In engineering data work, records for materials, sensors, or suppliers are often structured but incomplete. Using checks, default values, or fallback options prevents missing data from breaking a workflow and makes data handling more robust. When working with dictionaries from sources like spreadsheets or lab instruments, use safe key access because fields may be named differently or missing. Instead of letting a missing value stop the workflow, handle it with a default value, a warning, or a request for more information. This keeps the analysis reliable and flexible, even when records are incomplete. Safe key access is part of sound data handling, not just a way to prevent errors. Missing values have different importance depending on context, so you should decide which properties are essential and how missing ones should be handled. Good workflows stay robust and transparent by continuing when appropriate while clearly flagging gaps, especially in academic, professional, or safety-critical settings where records may be incomplete or changing. Python code safe key access. Use safe dictionary access to avoid crashes when expected keys are missing. This is especially important for engineering records, which often have incomplete properties. Providing defaults keeps analysis clear, reliable, and robust. A pump record is created as a dictionary to store key details about a specific pump. It identifies the pump as P204 and records its maximum pressure as 850 kilopascals. This makes the pump data easy to access and manage, even when some details, such as efficiency, are not provided. This line stores a Celsius temperature value of 72 in the pump record. It adds this temperature as one property in the pump's data structure, making it easy to access or update later in the code. The code directly retrieves the maximum pressure value from the pump record, assuming that the needed key is present. It then prints a labeled message showing the pressure in kilopascals, confirming that the value was successfully accessed. Use the dictionary get method to safely read the pump efficiency value. It looks for the efficiency percent entry and returns not reported if the entry is missing, which avoids an error. The printed result is either the recorded efficiency percentage or the default message. The process begins by identifying the essential pump data needed for calculations: maximum pressure in kilopascals and temperature in Celsius. It then sets up a way to track any of these required fields that are missing from the pump record, so missing critical information can be found before calculations continue. The code checks each required key against the pump record. Any key that is not found is added to a list of missing items. This makes it easy to confirm that the record contains all essential data before further analysis. The code checks whether any required keys are missing. If none are missing, it reports the data as complete. Otherwise, it identifies the missing keys so the incomplete record can be fixed. A template string is created to summarize key pump data in a consistent format. It uses numbered placeholders for the pump identifier, maximum pressure, temperature, and efficiency. This makes it easy to produce a concise pump summary while allowing missing values to be handled safely later. A formatted summary is created from values in a dictionary using the format method. It includes the component ID and maximum pressure. And if either value is missing, it uses unknown instead. This keeps the summary clear and useful, even when some dictionary data is absent. The code safely reads the pump's temperature and efficiency values, using clear defaults when data is missing. If temperature is unavailable, it reports unknown, and if efficiency is missing, it says not reported. This lets the summary be created without errors while still giving useful information. The code prints a concise engineering summary for the pump, including its component ID, maximum pressure, temperature, and efficiency. It uses safe dictionary access, so missing fields are replaced with default values, keeping the output clear and reliable even when some data is incomplete. This script shows how to safely read values from a dictionary when some data may be missing. It directly retrieves values only when the key is known to exist, and uses a safe access method with a default message for missing fields, such as efficiency. It also checks for required information like pressure and temperature, then builds a clear summary using reported values or defaults. This makes the data handling more reliable and easier to understand when records are incomplete. String processing, string cleaning. String cleaning prepares text so it can be analyzed and reported reliably. In engineering data, inconsistent capitalization, extra spaces, or unnecessary characters can make the same value appear different. Cleaning standardizes the text by removing unwanted characters, matching case, and trimming whitespace before further processing. String cleaning often starts by removing extra whitespace and standardizing capitalization. Even a stray space or inconsistent letter case can make matching and grouping fail, because computers compare text exactly. Applying these rules early helps prevent duplicate categories and supports more accurate analysis of inspection results, part names, and similar data. String cleaning prepares text for later processing by removing or replacing disruptive characters, such as attached units, commas and numbers, status notes, or extra labels before values. It must be done carefully, because some characters may carry meaning, like a hyphen in a code or a negative number. Good cleaning combines technical skill with domain knowledge to keep data accurate, consistent, and ready for engineering workflows. Python code, string cleaning. Clean text is important before analyzing engineering data. Small examples can make string methods easier to understand, and dictionaries provide a practical way to store cleaned engineering records. We begin with a small list of messy engineering record entries. Each entry includes equipment, material, and measurement information, but the text contains inconsistent spaces, tabs, and line breaks. This sample data gives us a simple way to demonstrate how string cleaning can make records easier to work with. The clean text helper function standardizes input text so it is easier to compare or process later. It removes leading and trailing whitespace, replaces tabs and new lines with spaces, and collapses extra spacing so words are separated by single spaces. Finally, it converts the result to lowercase and returns the cleaned text. Each raw entry is cleaned by applying the clean text function across the list. This removes extra spaces, tabs, and new lines, and converts the text to lowercase, so every string has a consistent format. The cleaned entries are then printed to confirm they are ready for further processing. The process creates a structured record from each cleaned entry. Each entry is split into parts using the pipe delimiter. Extra spaces are removed, and the parts are treated as equipment, material, and measurement. A record is then built with the equipment and material values, preparing the data for later processing or storage. The code cleans a measurement string so it is easier to store in a structured format. It removes pressure and temperature labels, standardizes the status label, and deletes commas. These replacements strip unnecessary text and punctuation while keeping the useful measurement information. The code trims extra spaces from the cleaned measurement text so the data is ready to use. It then stores the measurement in the current record and adds the completed record, including equipment, material, and measurement details, to the records list. This creates a structured set of engineering records from the raw input. The code displays the first 3 cleaned and structured engineering records. This lets you review each entry in an organized form and confirm that the data cleaning and structuring process worked correctly. The process creates a concise summary using the first record's equipment and material information. Each field is formatted with capitalized words to make the report easier to read and more professional before the final summary is printed. This script cleans raw engineering text and turns it into structured records for analysis. It standardizes the text, separates key details such as equipment, material, and measurements, and removes unnecessary labels or characters. The cleaned entries are stored as dictionaries. Then a few sample records and a short summary of the first entry are printed. The result is data that is easier to analyze and report. String formatting. String formatting makes raw technical data consistent, readable, and easier to interpret. It turns mixed labels, values, timestamps, and units into a predictable structure that engineers and automated systems can understand. Without clear formatting, even accurate data can become confusing, especially in large reports or datasets. String formatting helps present numerical values clearly when converting them to text. In engineering, it balances precision with readability, so data is neither overloaded with unnecessary decimals nor rounded so much that meaning is lost. Good formatting also includes units and context, such as the type of pressure being reported, which reduces uncertainty and makes each value easier to interpret. String formatting makes technical records consistent, easier to review, and simpler to validate. It helps important details stand out in inspection logs and design documents, such as failures, missing comments, part numbers, and descriptions. When strings are combined with structures like dictionaries and lists, good formatting creates a clear, readable layer that preserves meaning and improves usability in engineering workflows. Python code, string formatting. Format engineering values so reports are easy to read and compare. Use formatted text with clear labels and units, and combine each record into a consistent line of output. An engineering record can be represented with a dictionary that stores labeled values for a sensor reading. In this example, it records pump A as the sensor, a measurement of 12.3456, and millimeters per second as the unit. This makes the sensor data structured and easy to access. The record dictionary is updated with two new entries. One stores the status as the uppercase word warning, using the UCR method for formatting. The other stores a timestamp string, giving the record a specific date and time for tracking when the event or data was recorded. The report line begins with the record's timestamp, followed by a vertical bar separator. It then adds the sensor name, left aligned in a field of at least 8 characters, so reports stay consistently formatted and easy to read. The code formats each record's value, so it appears clearly and consistently in the report. It shows the number with 2 decimal places, aligns it in a fixed width space, adds the unit, and then includes the uppercase status. Together, these details create a neat, readable line for each engineering record. A small collection of measured values is set up as floating point numbers, and an empty collection is prepared to hold their formatted text versions. The purpose is to convert each reading into a consistent, readable form for reporting. The process loops through each reading while tracking its position, starting the count at 1. For each item, it creates a consistent text line with the point number and the reading rounded to 2 decimal places, using leading zeros for alignment. Each formatted line is added to a collection for later use. The code prints a brief introduction, then displays a neatly formatted engineering record with its timestamp, sensor name, value, units, and status. It then introduces a set of consistent readings and prints them together on one line, separated by semicolons for concise, readable output. This script shows how Python F-strings can turn engineering data into clear, readable console reports. It formats a single sensor record by emphasizing the status, aligning the sensor name and measurement value, and including the unit and timestamp. It then applies the same idea to multiple readings, using consistent formatting and leading zeros for uniform output. The main takeaway is that F-strings make structured engineering reports easier to read and present.
Formatted strings.
Formatted strings turn raw data into clear, useful technical messages. In engineering, they help present values like sensor readings or material names within meaningful sentences or reports. For example, a raw number can be shown as a rounded temperature at a specific location, reducing ambiguity and improving communication for engineers and decision-makers. Formatted strings help combine different kinds of data into clear, consistent text. They let you control details such as number rounding, separators, units, dates, names, and timestamps, so the output is easy to read and interpret. This is especially useful in technical settings like engineering or manufacturing, where precision and consistency reduce confusion across platforms. Formatted strings help turn engineering data into clear, consistent messages for emails, reports, and alerts. When combined with basic data cleaning, they make information more reliable and easier to understand. This skill helps students communicate technical results professionally and reduce errors or misunderstandings. Python code formatted strings. Create clear engineering messages by combining cleaned text with rounded measurement values. Keep the wording short, accurate, and easy for beginners to understand. A dictionary is created to organize raw engineering data for later processing. It stores the equipment as pump A-17, the location as North Bay, and a pressure value of 486.728 kilopascals. Some text entries include extra spaces, which can be handled during formatting. The code cleans and standardizes values from a reading dictionary. It formats the equipment name by trimming spaces and making it uppercase, formats the location by trimming spaces and capitalizing each word, and leaves the pressure value unchanged because it is already numeric. Set the acceptable engineering pressure range from 450 to 475 kilopascals. The reading is checked against the upper limit. If it is at or below 475 kilopascals, the status is pass. If it is higher, the status is check, meaning further inspection may be needed. The message summarizes equipment status in a clear, formatted sentence. It includes the cleaned equipment name, formatted location, rounded pressure reading, rounded upper pressure limit, and a status showing whether the pressure is acceptable or needs attention. Create a consistent report line by showing the equipment name, location name, and pressure value in a fixed order. Clean the equipment and location text. Then format the pressure to 2 decimal places with thousand separators and the unit kPa. This keeps the report clear, uniform, and easy to read. The code prints 2 user-friendly engineering outputs. It first introduces and displays a formatted status message with equipment, location, pressure, and status information. It then introduces and displays a shorter report line focused on equipment, location, and pressure, with the pressure shown to 2 decimal places. The script cleans and standardizes equipment and location text, then checks a pressure reading against set limits. It marks the reading as acceptable if it is within range, or flags it for review if not. Finally, it prints a detailed status message and a shorter report line with consistent pressure formatting, helping make engineering measurements clear and easy to read. Structured engineering records. Creating records. Engineering records often need to capture several related details, not just one value. A dictionary is useful because it stores each detail, such as an identifier, location, date, measurements, and notes, under a clear key. This makes records like material samples or sensor readings easier to read, update, and understand over time. Engineering records often begin with text such as labels, serial numbers, and technician comments, so strings must be cleaned before use. Standardizing details like spacing and capitalization, and splitting combined fields into meaningful parts, helps create consistent records. This makes the data easier to retrieve, compare, and analyze later. Lists make engineering dictionaries more useful by letting one key store several related values, such as repeated measurements or standards. This allows a record to combine fixed details, like a station location or part number, with grouped readings or quality checks. Using dictionaries, lists, and strings together creates organized records that support technical decisions and clear communication. Python code. Creating records. Create one organized engineering record by combining dictionaries, lists, and strings into a single structure. Before storing any text values, clean the strings so the record stays consistent and reliable. The code begins with raw engineering data that will be cleaned and organized later. It includes an unformatted equipment tag, a condition note that needs cleanup, and a set of millimeter measurements recorded for the equipment. The code standardizes an equipment tag by trimming spaces and converting it to uppercase. It then separates the tag into its main identifiers using slashes, cleans each part, and stores them as the area, system, and component. This makes the equipment information consistent and ready for accurate categorization. The code standardizes the inspection note by trimming extra spaces and capitalizing it. It then averages the millimeter measurements and uses that result to judge the component. If the average is 12.05 or less, the component passes. Otherwise, it is marked for review. We create one structured dictionary for the engineering record, bringing together the cleaned area, system, component, measurement list, rounded average measurement, inspection status, and standardized note. This keeps all key inspection information in a single record that is easier to access, manage, and review. The output presents a structured engineering record with key details about an inspected component. It shows the component name, its location based on area and system, the raw millimeter measurements, and their average rounded to 3 decimal places. It also reports the inspection status and includes a cleaned note with any additional observations or instructions. The script turns raw engineering data into a clean, structured record. It formats the equipment tag and inspection note, separates the tag into location and component details, averages the millimeter measurements, and assigns a status based on the limit. It then stores the key fields and prints a concise summary showing the component, location, measurements, average, status, and note. Record lists. A record list stores many structured records, with each record describing an engineering item or event using consistent fields. This is useful when a project includes many components or tasks, because each entry can keep details such as an identifier, location, and status. Organizing records this way makes engineering data easier to review, compare, and analyze. Record lists combine dictionaries and lists to organize structured data clearly. Each dictionary names its fields, while the list collects related records into one consistent set. Standardized strings for names, results, and statuses make the data easier to search, report, and communicate. Well-structured record lists make data easier to process, analyze, and share. Using consistent keys and predictable formats allows records to be filtered, grouped, sorted, and summarized for reports, dashboards, or later export. Each record stores one specific engineering detail, while the full list creates a clear, searchable collection that improves accuracy and supports future work. Python code. Record lists. Create structured engineering records by combining dictionaries, lists, and strings. This helps keep information consistent, organized, and easy to search. The code begins with a list of raw inspection notes, where each note describes equipment details such as its identifier, location, material, and status. Because the notes use inconsistent spacing and capitalization, they need to be cleaned and organized into a more structured format for later processing. We start by creating an empty records list to store structured inspection note data. As each raw note is processed, a dictionary can be added to this list, keeping the results organized and consistent. The process converts raw inspection notes into structured records. Each note is separated into fields, cleaned for consistent spacing and capitalization, and checked to make sure it contains 4 parts. Valid notes are then stored as dictionaries with an uppercase ID, location, material, and status, creating a clean collection of usable data. The program prints a message, then displays the structured list of records. This shows that the raw notes have been converted into a consistent format, making them easier to review and use. It also helps confirm the data is ready for analysis or reporting. A list comprehension can filter records to find those needing attention. It checks each record and keeps only the ones whose status is not okay. The result is a smaller list of items that may need inspection, maintenance, or repair. The code announces that it will show records needing attention, then lists the records whose status is not okay. This makes it easy to find items that may need inspection or maintenance. The process takes the first structured record, creates a readable maintenance summary from its ID, location, and status, and then prints that summary so the record's condition is easy to understand. The script turns messy inspection notes into clean, structured records with fields for ID, location, material, and status. It then identifies which records need attention by selecting those whose status is not okay. Finally, it prints both the full set of records and the filtered results, along with a short readable summary of the first record. Record retrieval. Record retrieval means finding specific information in structured engineering data. Dictionaries store individual records with meaningful labels. Lists group many records into a dataset, and strings act as names or identifiers. When records are organized predictably, it becomes easier to answer practical questions, such as locating an asset record or identifying samples that failed a test. Retrieving records often means searching for entries that match conditions, such as a threshold or a location. Because text data can be inconsistent, strings should be standardized before storage or during retrieval to make searches reliable. This supports data quality and helps prevent safety or compliance issues from being missed. Structured record retrieval helps engineers analyze, summarize, compare, and share data effectively. Dictionaries, lists, and strings organize records so teams can access information clearly, whether for reports, quality checks, or other engineering tasks. A strong system uses unique identifiers for direct lookup, supports filtering across groups of records, and produces clear outputs for stakeholders. Python code, record retrieval. Use structured engineering records safely by organizing meaningful fields in dictionaries and grouping related record dictionaries in lists. No extra packages are needed to run the code. The script uses only Python's built-in features, so it can be executed without additional setup or dependency management. We create a list of dictionaries to store maintenance records in a structured way. Each record includes a tag, location, and status, such as items at plant A or plant B, marked either OK or check. This format makes it easy to access and update specific details for each maintenance item. Technical notes are added to each maintenance record to explain its status. One pump is marked OK after inspection found no corrosion, while a valve is flagged for checking due to minor corrosion near the flange. Another pump is also flagged because high vibration indicates it needs alignment, giving future reviewers clearer context for analysis and decisions. To find a record with a specific tag, set the target tag and filter the records for matches. If any matches are found, choose the first one. If not, return no selected record. This provides a simple way to isolate the desired record by its unique tag. The search term corrosion is cleaned by making it lowercase and removing extra spaces, so matching is consistent. The records are then filtered by checking whether each note, also in lowercase, contains that term. This keeps only the entries that mention corrosion. To filter records for plant A, first standardize the target location by making it lowercase and removing extra spaces. Then check each record's location in the same standardized way and keep only the matches. This creates a focused set of records for that specific location while avoiding issues caused by inconsistent formatting. The output summarizes key record counts for quick analysis. It shows the tag and status of the selected item, then reports how many records mention corrosion and how many belong to plant A. This helps engineers identify potential corrosion concerns and review records by location. The code goes through a combined set of records with corrosion notes or from plant A. For each record, it creates and prints a short summary showing the tag, location, and status, giving a quick overview of the relevant items. The code prints a completion message after retrieving the data. It includes the total number of records processed, giving a quick confirmation that the operation finished successfully. This script uses dictionaries and lists to manage maintenance records, with each record storing details such as tag, location, status, and notes. It retrieves one record by tag, searches notes for corrosion, and filters records from plant A. It then prints key counts and short summaries showing each record's tag, location, and status, confirming that the requested records were retrieved. In this lecture, you learn to use dictionaries to store and retrieve engineering properties by meaningful keys, process strings to clean, split, and format technical text data, and combine dictionaries, lists, and strings to build structured engineering records. In the next module, Module 3, we will go over functions and files.
Thank you for your attention. See you all in the next lecture.